saying my name is Juan Ehringer. He already introduced me. I'm a senior in Spruce Creek High School right now. This is my last and final year. And I was brought out here today to talk to you about a vision that I had during my sophomore year at school of building a car that could exceed the performance capabilities of a modern-day sports car, but at the same time be economically viable and have the efficiency of a hybrid sports car, or a hybrid car. So a lot of people ask me what made me do this project, and truth be told, I don't really know entirely. There's not one straight answer for that. There have been a lot of things that have contributed to me choosing this. When I first started off, I began by researching alternative energy sources for cars and power drives. And I saw everything from compressed air to compressed nitrogen, even like nuclear. But I decided to shy away from nuclear because I didn't want to grow an extra limb while driving. But a big encouragement for the actual car was my drive to school every day, which is about 22 miles each way. And I don't drive it personally. I have a carpool, and I don't drive because I have a car, but I took it apart. So I can't drive it, but every single day, me and my carpool conquer this 44-mile drive from our house to and back. And this has changed the way I look at vehicles, because you're using so much energy to transport yourself from point A, literally, to point B. And I made a chart to kind of help explain this, the price of electricity versus the price of gas. The gas S2000, which is the actual car that I chose, it's a small two-seater convertible. The gas S2000 gets an average miles per gallon of 19 miles per gallon. And so when you compute this, driving 44 miles a day, you'd use about 2.25 gallons of gas. So with gas prices at their current level, which is like crazy, $4.08 for premium, you're using $9 a day for gasoline, and over the course of one school year, which is like 180 days, you're using $1,600 worth of gasoline. And there's also a little chart on the bottom which will help explain it, but the electric S2000 uses only a quarter of a kilowatt hour per mile to drive, and a kilowatt hour at like FPL rates is about 7 cents off peak. So you're using $134 compared to the $1,646 of electricity and fuel to power this car compared to the gas S2000. And on the bottom, there's a little chart that shows a more conventional view of the price per mile to travel it using the two different types of cars and the cost per 100,000 miles. So the cost for 100,000 miles for a 19 mile per gallon car running premium fuel is $21,000, a little more than that. The price for an electric S2000 running 2 motors, just running off a battery pack, is under $2,000, which is a pretty good difference. Additionally, falling electricity costs make it better than ever to have an electric car because you're paying much less per kilowatt hour. Originally, in the 1990s, it used to be around $2.50 for a kilowatt hour, which if you guys paid that, you'd be paying a lot more for your electric bills. And now, in 2000, it's about 10 cents per kilowatt hour on average. So let me just go ahead and start. This is my car. I purchased it at the end of sophomore year. And it's a little yellow convertible, and it has 2 seats, and it weighs around 2,000 pounds, so 1 ton. And it was chosen because it has a large engine bay, which is one of the main reasons, so I could store the two motors. It also is lightweight, so to get more efficiency, and also it's pretty cool looking. So I started taking it apart almost the day I got it, because I didn't want to drive it. Taking it apart. Here are the motors coming out now. And there you go, it's gone. So what comes now? So once I got the motors, here are the two 9.25 inch brushed DC motors. They're relatively inexpensive, which is good, compared to AC, which costs you basically a couple of legs and maybe an arm. So the cool part about these motors is they have 1,500 foot-pounds of torque at 0 RPM, while a Corvette has about 300 foot-pounds of torque at some random RPM. So I started building a motor mount for these out of aluminum, and I soon realized that I was completely obsessive-compulsive, and once I got it in, I decided to trash it. And I learned CAD and began my life as an engineer by underpaying myself and overworking myself, and redid the entire mount. Now it's made out of 1/4 inch steel. So with that out of the way, I was able to get them in the car, which is good. And I began on the electronic components. So for the electric car, for an electric car in general, one of the main deciders of how much power you get out of your car is going to be your controller and your batteries. So the controller dictates how much voltage, how much current actually gets to the motors. And because I'm crazy, I decided to pick a 2,000 amp, 345 volt controller that can produce, if it was 100% efficient, it produced about 800 horsepower. So this picture kind of just depicts what's actually on the electrical box. We have the vehicle controller up here. It's water cooled because it gets really, really hot, so you can boil tea if you really want. We have the interface board, which takes all the inputs and outputs and translates it into the controller's language. You also have an inertia switch, which if you didn't know what that does, it senses when I crash the car to turn everything off. So let's hope that I don't have to use that. We also have a DC-DC converter, which takes the 345 volts from the main traction pack and turns it into 12 volts. It's a big conversion. So from there, I had to go into the batteries, and I had decided that since A123 stock crashed, I was able to get the batteries pretty cheap, much cheaper than they used to be, and I decided to adopt a 416 cell configuration with 4 in parallel, 104 in series, making about 345 volts, and each module can put out 2,400 amps for about 10 seconds. The battery will be about 27 kilo hours. The Nissan Leaf battery, which can travel 100 miles on range, has a 24 kilo-hour battery pack, so I should be able to get around 100 miles of range out of this vehicle. I started going back to CAD and continuing my life as an engineer. And the second picture on the right is a picture of the actual module inside the car. And I've got 2 boxes, which I'll show you later, but that's the module. And here are some power calculations, which I was obligated to put in. And when you calculate the amount of resistance in the cells themselves, the internal resistance, as well as the resistance in the copper bars, and you go through all the formulas, you can get about 641 horsepower, which is about 470 kilowatts of energy out of the car itself. So multiply that by 80%, and you have about 600 horsepower. So with all this power, I had to upgrade the stock drivetrain system. I decided to get rid of the transmission because transmissions are lame. And I put a 8.8-inch Ford differential in there, and I drove it direct drive. So here's a picture of the stock S2000 differential right next to the Ford 8.8-inch. It's much bigger, as you can tell. So I got it in there. This is me underneath the car. And I cut the bottom of the car off. But I replaced it, so which is good. We're good. So now there's a box there. These will hold the batteries once the car's done, which it should be done in about 4 weeks. And it's located where the convertible top used to be because there was a huge space occupied by the convertible top. Once removed, there's a bunch of space, so I'm probably just going to end up using a hard top. In addition to all that, I like to do some other modifications to the car that I thought were cool and like electronic and nerdy. I replaced the stock taillights, which these are the stock taillights, with LED taillights. Ooh, really cool. And also, I'm designing and building an Arduino-based control system that uses a Nike Plus iPod foot pod and detects when your foot pod's moving, and it will open the doors for you when you get near the car. And on that note, I'd just like to say that electric cars are going to be the future, and all we really need to have electric cars as the future is better batteries and improved infrastructure. So here I have, let's see, this is about 15 fluid ounces of gasoline/water. It's actually water, don't worry. A 20 amp hour A123 pouch cell, and a lead acid battery. And if you look at this, a gallon of gasoline has 36.6 kilowatt hours of energy, which is a lot. It's a lot. So in my car, to go 100 miles, I have about 2/3 of a gallon of gasoline. This is about 4.5 kilowatt hours. This is 0.06 kilowatt hours. And this is like 1/10 of kilowatt hours. So like 34 of these is equal to this. So improved batteries will allow us to go farther on what we already have on our cars. And by building these electric cars, we can improve the future and hope that when the batteries do come out, all we have to do is swap them out. So let me just end by saying that when we do actually create a bunch of electric cars and we have everything set up, we should be able to run our world off of no direct CO2 emissions, and once we get renewable energy going, we can charge up using that. And I think that is an idea that can power our future. Thank you.